Hey everyone, welcome back to Real Analysis 1. This will be lecture 19 of the course. And in this section, we're going to continue our exploration of big theorems from calculus, but treated more rigorously since this is real analysis. And in this section specifically, we're going to look at L'Hopital's rule. So let's go ahead and jump into it. We'll call this section 5.3, L'Hopital's rule. Now you will recall L'Hopital's rule from Calculus 1. It's a theorem that instructs us regarding how to treat certain kinds of infinite limits and limits that are undefined or indeterminate. So we'll get into the theorem in a moment. Before we do that, we need a definition of an infinite limit. So let's start with that. We'll start with a definition here. Let's let f be a real valued function. Let f be a real valued function defined on a set E of real numbers. And we'll let P be a limit point at V. Okay. So P is a limit point in E, which is just a subset of real numbers. F is defined on E. Then we say that F approaches infinity as X approaches P if for all M real numbers, for all M and R, there exists a delta greater than 0 such that the value of the function at x is greater than m for all x in the set E where x is within delta of p. Where another way to say that would be 0 is less than x minus p less than delta. Okay, so this is the definition of this is what we mean by a limit evaluating to infinity, right? A function approaches infinity as x approaches some point. Right, so this would be like the obvious example here would be like asymptotic behavior. So the function, as x approaches a particular finite value, the function, blasts off to infinity or negative infinity. And so f approaches infinity as x approaches p if for all real numbers, there's going to exist some delta such that the function is greater than that real number whenever x is within delta of p, right? So meaning the function can get larger and larger and larger. All I have to do is get closer and closer and closer to p. Okay, and this is not usually this is kind of shorthand here. We typically would denote this as just the limit as x approaches p of f of x equals. And instead of a finite value, we write infinity. And so this is the definition for a positive infinite limit, but then an analogous definition can be given for limits at negative infinity. So I'll leave that to you. But so this is something we'll need because L'Hopital's rule deals with cases where limits maybe are infinite. And so let's recall what L'Hopital's rule is useful for. Let's recall kind of what it says. So L'Hopital's rule is useful. It's useful for evaluating limits of the form, and there's a couple different forms here. So think about it like this. We've got, it's useful for evaluating limits of the form, the limit as x approaches p of a ratio, f of x over g of x. All right, and we would say specifically where the limit of f is equal to the limit of g, which is equal to 0, or the limit of f is equal to the limit of g, which is equal to plus or minus infinity. And so these both give you what are called indeterminate forms. Indeterminate form, and in this case it's 0 over 0. You're just not sure what what's what here. And in the same case here, this would be called the indeterminate form of infinity over infinity, plus or minus. Okay, so we say these are indeterminate because, I mean, basically prior methods don't really hold in these kinds of extreme cases. Right, so these are indeterminate because prior methods do not hold in these extreme, and I'll say extreme, cases, right? Because, hey, if you have to divide by 0 or infinity, then you're obviously dealing with some kind of an extreme behavior, right? Okay, so that's the idea, right? So whenever we have a function that is a ratio like this, and we're trying to identify the limit as x approaches a particular value p, and we run up against one of these types of indeterminate forms, 0 over 0 or infinity over infinity, we need to know how to deal with this, and that's what L'Hopital's rule addresses. So let's go ahead and state the theorem, and then we'll prove it. Okay. So here's the theorem, and there are different ways to state L'Hopital's rule. There are more or less complex ways to write it. We're gonna start with like the most real analysis-y, the most real analysis-esque, I guess I should say, statement of the theorem. And that's the one we'll prove, and then afterwards we'll discuss how it can be said in different ways. So this is L'Hopital's rule. Okay, so suppose f and g are real-valued differentiable functions on the open interval AB with g prime of x, the derivative of g, not equal to 0 for all x in a b, right? So what we're gonna basically say f over g is the real function. It's a ratio. It's a rational function, and we need the derivative to not be non-zero on the interval. So this is the setup. So f and g are real value differentiable functions on an open interval AB with g prime of x not equal to 0 for all x on the interval, where negative infinity is less than or equal to a, which is less than b, which is less than or equal to infinity, right? So this is just basically saying any interval but a is less than b. Okay, and then we say suppose that the limit as x approaches a from the right-hand side of f prime of x over g prime of x equals L, so some limit of the derivatives of the function, where L is a real number, but also could be positive or negative infinity, right? So the limit exists, and it could potentially be an infinite limit, right? So I've got the derivative of the rational function here, the derivative of the numerator, derivative of the denominator, equals, I can identify that limit, right, as either a real number or an infinite limit. Then, right, so these are all the conditions. And then there's an additional condition. If 1, the limit as x approaches a plus of f of x equals the limit as x approaches a plus of g of x equals 0. So either I get the indeterminate form of 0 over 0, or 2, the limit as x approaches a plus of g of x equals plus or minus infinity. then, right, so either one or two condition applies here, then the conclusion is that the limit as x approaches a plus of f of x over g of x is indeed equal to whatever this guy here is. It's equal to the limit of the ratio of the derivatives. Okay, so this is a little bit more wordy. This is a little bit more. It's a different expression of L'Hopital's rule than what you probably encountered in Calc 1. But that's mainly because the proof of it requires just a little more precision in the statement. Now, in practice, what you can think of this as is just, hey, look, if I've got a rational function f over g, and the limit when I look at that limit and I take the limit of the numerator, the limit of the denominator separately, and I get an indeterminate form, then usually what you'd say is you just fall back and say, okay, well, L'Hopital's rule says if I can differentiate the top and the bottom, and the derivative of the bottom is never zero, and I get a sound limit out of that, then that limit is the limit of the undifferentiated version, right? And so that's the way you kind of, it's expressed to you in Calc 1. Here it's just got to be a little bit more, it's really the same thing, it's just here we're going to deal with the right-hand limit just because it makes the proof easier, and also it just has to be stated with a little more precision. But it really is the same theorem, and hopefully that's clear. Okay. Very good. So let's go ahead and prove this theorem. Now I will warn you, this is probably going to be maybe the hardest proof of the course, and that's kind of by definition. It's the second to last lecture in real analysis, one anyways. And so this is a very, very involved proof. It'll probably take us 20 to 25 minutes to even walk through it. And so just, prepare yourself because it's a tricky one. It's a little bit tricky. But let's go ahead and do it. And let's start. Okay, so this will be the proof of L'Hopital's theorem. So what we're going to do is we're going to assume, obviously we're going to assume all of this business here. And then we're going to kind of prove it with cases. We're going to start by assuming that this is the case. And then after that, we'll jump into the second case, right? So we'll start with the first case, which I tend to think is the easier case. And then we'll go to the second case. Okay, so we'll assume the conditions of the theorem. And assume that 1 holds. Namely, we have the indeterminate form of 0 over 0. Okay. All right, so we'll assume that 1 holds, and I guess I'll just state it that the limit as x approaches a plus of f equals the limit as x approaches a plus of g, which is equal to 0. So you get the 0 over 0 condition. Okay, and so we're going to prove this case here specifically where a is finite. Now we'll secondarily deal with a being an infinite number, right? Because it does say that a and b could be, they could be infinite numbers. Right, so let's start. So we'll assume that a is finite. Okay. All right. Let's go ahead and let x of n be a sequence in AB with x of n approaching a and x of n not equal to a for all n, right? So you got some sequence in this interval, and the sequence converges to a as n goes to infinity. But it's never equal to a. Okay, we'll assume that. Okay, and then let's set f of a equal to g of a equal to 0. Okay, all right, and so then here's where the mean value theorem starts to come in. So by our assumption, 1, f and g are continuous at a. F and g are continuous at a, and therefore, by the mean value theorem, for each n natural number, there exists a Cn. And that Cn is going to be between a and x of n, right? So I've got this sequence of xn numbers that approach a, and for each one of those I can always find a Cn between a and x of n. And so for each n in n there exists a Cn, and that can be, so this is all due to the mean value theorem, right? And so for each n in n there exists a Cn in this interval such that g prime of Cn times f of xn minus f of a equals g of xn minus g of a times f prime of Cn. Or a better way to state it might be f of xn over g of xn equals f prime of Cn over g prime of Cn. Okay. All right. Okay, so we've got that kind of from the mean value theorem. Now note, g prime of x, well, so since g prime of x is not equal to 0 for all x in this AB interval, g of xn equals g of a for all n. Okay. As n goes to infinity, Cn goes to a plus, and by theorem, and obviously what we're assuming and assumption, we have this, the limit as n goes to infinity of f of x over f of xn over g of xn equals the limit as n goes to infinity of f prime of Cn over g prime of Cn, which is equal to the limit as x approaches a plus, right? Because remember, the xn's go to a, right? So this is equal to the limit as x approaches a from the right of f prime of x over g prime of x, which is equal to L. Okay. Now, because this holds for every sequence xn, the result just follows from that, doesn't it? So this holds for every sequence xn, right, where, well, I mean, obviously xn has to approach a plus, right? But this holds for every sequence like that in this interval, and so therefore, the limit as x approaches a plus of the ratio f to g must be L. Okay, perfect. So that gets us the proof of 1. Okay, now the next part of the theorem I think is the harder part. This one is, I mean, this one has some fairly, I mean, I think it's fairly straightforward, more or less. If you understood the mean value theorem, you're just kind of taking that, plugging in something in between, and it all kind of follows from that. But part 2 is a little trickier, I think. So let's assume next that the second condition holds. Right, what is that one? Remember, i.e. that the limit as x approaches a plus of g of x is equal to infinity. Right, so you've got somehow that denominator blows up as x approaches a, and really the case where g approaches negative infinity is analogous, and so we'll look at this case, and this one will be fine. Okay, so this is, now we're going to kind of start with the second condition and prove that that one also implies the same thing. Okay. So let's assume that negative infinity is less than or equal to L, which is less than infinity. So the limit is, somewhere here. And we've got a beta, a real number, where beta is greater than L. Okay. So you've got this hypothetical limit that's in this interval. It's greater than or equal to negative infinity, less than positive infinity, and beta, a real number, is greater than L. And let's choose then. So let's choose R such that R is between L and beta. Okay. All right. So you've got this L, you've identified a beta, a real number that's larger than L, and you're just selecting an R between the two values. Of course, that's always possible. We're dealing with an interval here. Okay. Now, since the limit as x approaches a from the right of f prime of x over g prime of x is less than r, right, there is going to exist a c in the interval ab such that f prime of gamma over g prime of gamma is less than r. And this is going to be true for all gamma where gamma is between A and C. I'm going to call this C1 actually, okay? Because we'll have to construct a series of these, or a couple of them. Okay, so you've got this ratio of you get the limit as x approaches a of f prime of x over g prime of x is going to be less than r. That implies that there exists this c1 in the interval such that this is true. Okay. So what we want to do is we're going to then use this to construct this second piece here. So then let's fix y, and we want y to be between a and c1. Okay, so we're going to fix some y between a and c1. And then since g of x goes to infinity as x goes to a plus, there's going to exist a c2, right? And this c2 is going to be between a and y. All right, so we're going to narrow this up. Right, so we've got y between a and c1, and now we're going to find a c2 between a and y. Okay, so there exists a c2 between a and y such that g sub x is greater than g sub y, and g sub x is greater than 0 for all x where x is between a and c2. Okay, so I'll put it on the screen here. Okay, all right. So there's a little bit of linkage here, so make sure you're kind of following this up. Make sure you're following this argument. It's a little bit tricky. Then let's let x in the interval a to c2 just be arbitrary. Okay. And by the mean value theorem, there's going to exist a delta between x and y such that f of x minus f of y over g of x minus g of y is equal to f prime of delta over g prime of delta, and that'll have to be less than r. Okay, this guy here is less than r from up above, and this is the mean value theorem. Okay, so we've got this. And now what we're going to do is we're just going to basically manipulate this expression, and it'll get us what we need. Okay, so we're going to multiply through. I'm going to switch pages here. We need a lot of space for this next part. Okay, so we've got f of x minus f of y over g of x minus g of y equals f prime of delta over g prime of delta, which is less than r. Okay. So what we're going to do is we're going to multiply through by g of x minus g of y over g of x. Okay, now this is obviously going to be greater than 0, right? And so what do we get? So okay, I'm going to write it out to make sure people follow the derivation. G of x minus g of y over g of x. And we're going to multiply that by f of x minus f of y over g of x minus g of y. So we get that. That's going to be less than this r over here. R times this expression, g of x minus g of y over g of x. Okay. And so what do we get there? Well, this simplifies down, so this obviously cancels, and we have this piece. F of x minus f of y over g of x is less than r times, and we can rewrite this as 1 minus g of y over g of x. Okay, so just kind of simplifying that ever so slightly is helpful. Okay. And then we can break this up here, and so this would be f of x over g of x minus f of y over g of x is less than r times 1 minus g of y over g of x. And we can just move some things around here, and so I want the f of x over g of x over on this side, and that's going to be less than r times 1 minus g of y over g of x plus this one, f of y over g of x. And this is going to be for all x, where x is between a and c2, if you recall. Go back and double check that. Okay, so we've got this expression. So f of x over gx, and remember that's the thing we're trying to find the limit of, it's got to be less than r times 1 minus g of y over g of x plus fy over g of x. And this is true for all x in this range between a and c2. Okay. All right, so a little bit tricky, but hang in there. We're getting close to the end here. We're getting close. Okay, so we've got this thing, and now what we're going to say is for a fixed y, since g of x goes to infinity, here's what we get. We get the limit as x approaches a plus, a from the right, of f of y over g of x. This is going to be equal to the limit as x approaches a plus of g of y over g of x. And this is going to be equal to 0. Right? Okay, and so that's these two pieces, isn't it? Yep. And so therefore, shift pages again. Therefore, the limit as x approaches a from the right of f of y over g of x plus r times 1 minus g of y over g of x. All right, so that's just that right-hand side. The limit as x approaches a, we know that this goes to 0 and this goes to 0, so this is just equal to r, which is, remember, less than beta. All right. Okay, so given that, there must exist a C3. And in this case, C3 is going to be greater than A and less than C2. Right? There's going to exist a C3 in this A to C2 interval such that f of y over g of x plus r times 1 minus g of y over g of x is less than beta. And this is going to be true for all x where a is less than x, which is less than C3. Okay. And we just saw previously that f of x over g of x was less than beta for all x where x is between a and C3, right? So all we're doing is kind of tightening that range a little bit, isn't it? Okay, all right. And so then, if L equals negative infinity, then for any beta real number, there exists a C3 such that the previous holds, right? The previous holds. Okay, and that's going to hold for all x between a and C3. Right? I.e., what am I saying here? I.e., I'm saying f of x over g of x is less than beta. Okay, and that's the definition of an infinite limit, right? So then by def, the limit as x approaches a from the right of f of x over g of x is equal to negative infinity. Now if L is finite, right? If L is less than infinity, well then there's going to exist an epsilon greater than 0. Okay. By taking beta equal to L plus epsilon, there exists a C3. There exists a C3 such that f of x over g of x is less than L plus epsilon for all x in A to C3. Okay. All right. One more piece. We're almost there. Let's suppose that negative infinity is less than L, which is less than infinity. Then let's let alpha be a real number with alpha less than L. Okay, alpha is just some arbitrary real number. Okay. And a similar argument is going to produce another value of C. So by a similar argument, there exists C3, and I'll just put C3 prime in AB, such that f of x over g of x is greater than alpha for all x where a is less than x less than C3 prime. Now what happens if L is equal to infinity? Well, if L is equal to infinity, then the above, well, it just kind of follows from what we just said, right? If L is equal to infinity, then the above argument implies that the limit as x approaches a plus of f of x over g of x is equal to infinity. But if L is less than infinity, then taking alpha to equal L minus epsilon gives the existence of C prime 3 such that f of x over g of x is greater than L minus epsilon for all x where x is between a and C3. Right? And in this case, the limit as x approaches a plus of f of x over g of x equals L. Right? And that's all the cases. That's the last. So the last case was, yes, if L is indeed even equal to infinity, then you have the same result. So that's L'Hopital's theorem, and that's the proof of L'Hopital's theorem, L'Hopital's rule. Now, something to note is that we prove L'Hopital's rule using right limits. Now, you could just as easily prove L'Hopital's rule using left limits. Okay, so in this case, we used right limits. Okay, we used right limits in the proof. You can also use left limits. Okay, you can also use left limits. And what that really implies is that the statement of L'Hopital's rule can be stated in terms of overall limits, and you can drop the left-hand right-hand notation. Right, the left and right hand limits are useful in the proof, as I say. Like certain things, if the ability to approach a value from a direction makes the proof more straightforward. You can easily write the proof approaching from the negative side as well, and it changes very little. And that being the case, the statement of L'Hopital's rule can be made using just overall limits, not having to rely on the left and right hand limits, which is more like what you encounter in your calculus class. When you first encounter this, it's not expressed in terms of left or right hand limits, it's expressed in terms of overall limits. And so you can go back to that first definition that we had of L'Hopital's rule, this one right here, and all of these areas where right here, where we talk about the right approaching a from the right hand side, that can all be dropped, and instead we can say x approaches a, period, right? Because you can prove it from both directions, so overall it must hold. Okay, and so that's the last piece of the class would be to rewrite L'Hopital's rule, but expressing it in terms of overall limits rather than in terms of approaching from the right-hand side or the left-hand side. Okay, very good. Now, I know that was a very tricky proof. Spend some time on that one. Make sure you understand it. As I said, it's probably the most complicated proof of the course, I would say, probably close to. And so next lecture will be the last lecture of real analysis, and in that section, we're going to take a look at Newton's method, which is something that is a little bit different. I like to go through it because I find it very interesting. A lot of analysis course will skip over it, but in this one we're going to have one last lecture where we do explore Newton's method. So until then, take care.